All right, welcome, folks. Hopefully, people can hear me now. Not sure if the mic is live. See, yeah, I think it's working a bit better now. Okay, so I'll see if I can put that into the classroom. Copy link address. Get that into classroom. All right, and then we'll see what happens from there. All right. Here we go, folks. We're going to wait for there to be a few people in the chat. I see we've got 2 so far. I want to give it another minute or so. Thanks for negotiating through to make sure that you found the stream. I'm using a new computer here for the streaming, so I hope that will make things a little smoother. But it means that it does not have a built-in microphone, so I've had to adjust the microphone settings, and they weren't working on the first stream, which is why I've switched over to this one. So give it another 30 seconds or so, and then we'll get started. If you can just type a 1 in chat if you can hear me. And if it needs to be louder, let me know. I can see if I can try to make things a bit better. Can you hear me? Oh, good. Thanks, Rumaisa. That's really helpful to know. All right. So I think we're going to get started then. Sounds like people can hear properly. Welcome to the 20th day of remote learning. Today's joke is, what kind of shoes do ninjas wear? Sneakers. Happy Monday. Simplify that like button to show your support. Thank you to Alan for today's joke. If you have a joke to suggest, please email it to me. I hope you enjoyed the Primer YouTube channel that we shared on Friday, and also hopefully the Primer movie. Today's YouTube channel is one called Smarter Every Day. I think a lot of you have probably seen it before. They do some really good videos about science, and they just did a great video about flocking behavior in birds and how to simulate it on computers, which is something that I've done a little bit of programming around. So I thought it was really interesting. The visuals are really cool as well. Today, we're going to talk about instantaneous rate of change again. We're going to look at them in rational equations or rational functions and in logarithmic functions. So with that, let's jump right in. In the classroom, there are 2 documents I'd like you to open, 3.16H and 3.16H3, and we'll deal with them in that order. All right. So instantaneous. Instantaneous rates of change for rational and logarithmic functions. All right. So we're looking at 3.16.h. This is the rational functions handout. It has a situation where the snowshoe hare population for a newly created conservation area can be predicted over time by the following model. P of t equals 2,550 t squared plus 1250 over 25 plus t squared. P represents population size, so the number of hares, and T is the time in years since the conservation area was open, and it's valid in the range from 0 to 50. So we're going to be taking a look at this equation and using it to calculate how fast the population of hares is changing, both for average situations and for instantaneous ones. All right, so let's dive in. So question A asks us to determine the average rate of change in the hare population for the first 10 years that the park existed. And then, equally important, to interpret what that means. So, rates of change, we're often in mathematics going to be using them in applications. So, it may be engineering or science. So, we always want to be able to understand what is the meaning of the math that we do. All right. So, if we're looking at the first 10 years, that means T0 is no years and T1 is 10 years. So we can go ahead and figure that out. Average rate of change is the slope formula. So it's P1 minus P naught over T1 minus T naught, or you might do it with Y2 minus Y1 over X2 minus X1, whatever you want. It's the same formula either way. So now we need to calculate those values, which means we need to find our calculator. There it is. And we're going to sub some values in. So for 0, it's very easy here. We're going to get 1250 divided by 25, because T being 0 is going to make this term and this term 0. And so we get 50. So P of T0, which we're also calling P naught, is 50. P of T1, which we're also calling P1, we need to evaluate. So we have 2550 times 1 times 10 squared plus 1250. And then we need to divide that by 25 plus 10 squared. So we get 2050 for P1. So then we just need to sub those in. We get 2050 minus 50 over 10 minus 0, which is 2000 over 10, which is 200. Okay. So if you can give me a 1 in the chat if that calculation is making sense. Thank you, Ramesa. All right. So we're taking a look here. The next question is, what does this mean? So I'd like you to take a look at the calculations we've done and just type into chats, what are the units for this number 200 here that indicates the rate of change? What units does this number have, this 200 number? I'll give you a moment, let you type that into the chat. Thanks, Ramisa. And that is indeed what it is. This is 200 hairs per year. And I just want to check the question and make sure that we are talking about hairs. Yes, we are. Okay. So 200 hairs per year, that's what this 200 number means. So it's telling us how fast the population of hares is changing. And so if we want to say what is the meaning of this number in this situation, it's telling us over the first 10 years, the population of hares increased by an average of 200 hares each year. So there's a few things about this that are important. The first one is that whenever we talk about the meaning of a rate of change, we want to specify when that rate of change applies. So here we've calculated a rate of change over the first 10 years. So we're going to include that in our statement. This is over the first 10 years. We've also got the number, of course, which is what most people will say. And we are including the units. So this is hairs per year or hairs each year. Very important to have the unit included. And the final thing that's really important is to say that this is an average rate of change. We're not talking about the population at 10 years. We're talking about the average rate of change over the first 10 years. So time period, if it's average, we need to state that. And then the unit hairs per year or hairs each year. Those are important things to include when you're writing this kind of answer. Okay. So between 10 and 15 years after the park opened, well, we could do the exact same calculation here, but with T10 or 10 for T0 and 15 for T1, follow through with our calculations for the populations and go through. I don't want to do exactly the same thing with you. So I do want to tell you we can do a little bit of an estimate here by looking at the graph and getting the numbers for T10 and T15 from the graph. And we can see that it looks like it went up about 50 hairs total over that time, because T10 was a little above 2,400. T15, the population was a little bit, not 2,400. Yeah, 24. Oh, no, I'm reading this incorrectly. So that is 2,000. So it went from a little bit above 2,000 to a little bit above 2,250. So we've had a rise of about 250 hairs over the 5-year period. Okay. Moving to the next handout here, or not, sorry, the next handout, the next question in the handout, it's asking us to estimate instantaneous rate of change this time. So we're looking at question C, and it is at 5 years. So at t equals 5. We're not looking for an average over a longer period. We're looking at that exact moment that the 5th year finishes after the park opened. So when t is exactly equal to 5, because remember, for the first year, t starts at 0, it ends at 1 at the end of the first year. So when t equals 5, we are 5 years after the park opened. Okay. And we're asked to use a centered interval method. You'll remember that this year we've only done the centered interval method. We haven't done the difference quotient. Both methods give you the same answer. When you do calculus, you'll see that there is a tiny difference between them, and that the centered interval method makes a lot more sense for certain situations basically when the function's discontinuous at the point that you're interested in. So we're going to continue to use it. So we're going to say t0 equals 4.999, so slightly below 5, and t1 equals 5.001, slightly above 5. So now we want to figure out the rate of change on the basis of that. So we need to know what is p of t0. Well, plug it into the calculator here. We get 2550 times 4.999 squared plus 1250 equals divided by 25 plus 4.999 squared. And there we go. So we get 1,299.75. And this is in hairs. So it's a little bit weird to have 0.75 hairs. But obviously, we're using a continuous function for a number that can only be a whole number. So it's just going to be an approximation. And that's often the case with mathematical models, that we have an approximation of the answer. So P of T1. Well, now we're dealing with 5.001. So we'll do our same calculation. 2550 times 5.001 squared plus 1250 equals divided by 25 plus 5.001 squared, and we get 1300.249975. So I want to take a look here. If we round this 1300.25, I want to take a look at the calculation with rounded numbers and with non-rounded numbers. This is something that students often have teachers be like, don't round until the very end. And students are like, why? It doesn't change the answer. Who cares? So I want to take a look in with this one and see how much of a change in the answer we get. So if we are looking at the slope, that's P of T1 minus P of T0 over T1 minus T0. And in this case, that is 0.5 after we do the subtraction. So this number minus this number divided by 0.002. And put that into a calculator. And we get 250. So now if I do this with the more precise numbers, so I'm just going to put this back into the calculator here. I'm going to recalculate PT0 with full precision. So we'll get 2550 times 4.999 squared plus 1250 equals divided by 25 plus 5.001 squared. There we go. Oh, clearly I have messed something up somewhere because I got a different number. Let me double check that. 2550 times 4.999 squared plus 1250 divided by 25 plus 4.999 squared. There we go. Okay, so I have this number, subtract this one times -1 because I did the subtraction backwards. So we also get 0.5 and we'd get the same answer. So in this one here, if we round early, we're still going to get the same answer. We obviously need to be careful about doing that, but in some cases you can get away with it. Okay, so this again, hairs per year is our set of units. And so now if we want to answer the question, 5 years after opening, what is the instantaneous rate of change and what is the meaning of this? Therefore, at exactly 5 years, after the park opens, just want to make sure I'm not going off the bottom here. It opens. The population is increasing by 250 hairs per year. And so you can see again, I've included my units. I've stated the time frame here, exactly 5 years after the park opens. And I haven't said that this is instantaneous, the way I said that it was average for the previous calculation, but I do say at exactly 5 years. And that is a way to indicate that this is an instantaneous rate of change. Okay, I'll pause it there. If that's making sense to you so far, please put a 1 in the chat. If you have questions, now is a great time to ask them. And we're going to be moving over to the second handout, the one on logarithmic rates of change, in a moment. Thanks, Rumesa. All right. So I will try and keep an eye on chat. If you have a question, please put it in there. If you can switch over to the handout on rates of change for logarithms and scroll down to the very last page. That's the one we're going to work on. Okay. So let me get this centered up. So log rates of change. I think you will find it unsurprising that we continue to use the same slope formula for rate of change and the same idea of finding instantaneous rates of change by sandwiching very closely a point. So the example we're looking at, so this is page 4, example 2. Scientists in a laboratory company raise amoebas to sell to school for use in biology classes. They predict the number of amoebas in a sample with the formula n of t equals 550 log base 10 of t, where t represents time in hours it takes to produce n number of amoebas. So we're again dealing with a population here. This population going to work a little differently than the last one. It's a logarithmic function instead of a rational one. So question A, calculate the average rate of change from t equals 3. So we'll set that as t naught to t1 equals 8. So to do that, we're going to have to calculate n of t naught. 550. Oh, I just heard a refocus there. Yep. Okay. So 550 times log base 10 of t naught, which is 3. gives us 262.4166901. And n of t1 equals, well, we have to do the same calculation, 550 times log base 10 of 8 this time, which is 496.6994928. All right, and so then for the rate of change, we will have n of t1 minus n of t naught over t1 minus t naught, which is that long number there, minus 262.4166901 divided by 8 minus 3, which is 5. And so we get approximately 46.86. Since we're talking about amoebas here, and this is amoebas per hour, this is really about 47 amoebas. So we're writing our conclusion. On average, between 3 hours and 8 hours, the population of amoebas grew by 47 amoebas per hour. All right. So there is something missing from this statement. Can you spot what it is? If you see it, type it out in chat. Right on. So grew by 47 amoebas per hour on average. And I guess I'm being a little picky here. We did start with on average. That would be sufficient. We do want to make sure, though, that we're clear that this is an average number. We have our units. We have the time frame, 3 to 8 hours. So we're good to go. All right. Final one for today. We want to use a centered interval to estimate the instantaneous rate of change at exactly 3 hours. So we're going to use a T naught of 2.999. We use a T1 of 3.001. You might be wondering why I'm choosing to use 3 decimal places. For most things, 3 decimal places is going to give us a reasonable estimate. You could make an argument for more decimal places. You can make an argument for fewer. As a general introduction to the topic of instantaneous rates of change, 3 decimal places is fine. In calculus, we learn a technique for doing this with infinitely many decimal places, which is obviously going to give us more precise answers than what we're doing here. There are other benefits as well to the methods from calculus, but we need to understand this method first before calculus is going to make sense. Okay. So we need to do the same calculation, n of t0, n of t1. Plug those into calculator. So we get 550 times log of 2.999 equals 262.3370562. And for T1, we go 550 times log base 10 of 3.001, and we get 262.4962975. All right. And so then when we go to calculate the slope, n of T1 minus n of T naught over T1 minus T naught. And if we do the subtraction here, 0.337056 minus 0.49622975. So just doing the calculation, the subtraction of these two. And again, I did it backwards, so I'm just going to multiply by -1. So we get 0.1592413 divided by, and this minus this is going to be 0.002, which gives us 79.62065. And we can conclude from that at exactly 3 hours, the population of amoebas grew by about 80 amoebas per hour. So we have the time, we have the unit, we have the word exactly indicating this is an instantaneous rate of change. And so that concludes that question. So homework is to take a look at the 3 homework questions on the logarithms page. I'm not going to assign any homework with the rationals. If you can do it for logarithmic ones, you can do it for rationals. It's just the exact same procedure. So please try the 3 questions there. These get into the meaning of the situations, which is really helpful for us. One last thing before we close up. If you do have a question, please type it into chat. If you don't, please type a 1. And one last thing before we close up. For people who have requested to participate in the assessment, if you filled out the information or filled out the form that I sent you, you should have received an email from me earlier today with your timing for your assessment. If you haven't filled out the form yet, please make sure that you do that and get back to me before Wednesday's class. So I really want to know before Wednesday's class so that I can make sure to get this organized. If you're not able to get back to me by then because you don't have information, please send me an email and let me know what your situation is. And that way we can figure out something that's appropriate for you. All right. Thanks a lot, folks. We will see you on Wednesday.